Hello AP Physics 1, it's Mr. Ng with part 2 of how to manage your rotational inertia data in Google Sheets. So if you recall the first time, our job was to confirm this equation. I, moment of inertia, is equal to some fraction times mr squared. And you kind of remember a lot of these fractions, like for the sphere, it was 2/5 mr squared. For a hollow tube or just two masses that are kind of far away from each other, it was just mr squared. And then for a disk, it was 1/2 mr squared, right? Remember all those little moment of inertia equations? You don't have to memorize them, but just know kind of the base of it is mr squared. So mass should be linear, and I hope you found that in your last data set. And r should be exponential, but it really depends on how you manage your data. A lot of us struggle. We just keep forgetting to make sure that you do your data with an order of magnitude, meaning if you start with 1 centimeter, you get to 10 centimeters, maybe 100 centimeters, at least 10 times bigger, if not 100 times bigger than your original data point. But here, I'm getting ahead of myself. Let's walk us through the math. So to get through the math, the first thing you need is you need the linear acceleration, right? And the linear acceleration, we found the equation is 2h divided by t squared. We found that equation with our trusty equation, 1/2 at squared. We know the height of the table. We know that the time that it took to fall down, so we can figure out the acceleration. Done. 1/2 at squared. After we do that, that's step one. We're going to find our torques. Our torque, we found the formula using free body diagrams and the sum of forces to be m times g minus a times r. All right, that's our torque equation. All right, just did a little bit of sum of forces. With that, we're going to combine that with number 3, our angular acceleration, so that we can find our moment of inertia, which is torque divided by angular acceleration. Good. So let's get into our sheet. Here, thank you, Jonah, for setting up this data. First, we need to find the tangential acceleration. So here, the tangential acceleration is equal to, let's remind ourselves, 2h divided by t squared. 2h divided by t squared, all right, is equal to 2 times h is equal to 0.9, that's right here, 0.9 divided by, I better do parentheses. This is a big common mistake. If you don't do parentheses, Google doesn't know the order of operations and it messes up. Divided by t squared, so I'm going to do parentheses again on the bottom, 9.15, do a little caret, 2, that's how you do squared, enter. Good. So my number came out nice and neat, but I bet your number looks like this, all long and ugly. So here, there's a way to make it look nicer. So here, first let's drag it down so that this formula gets repeated. So not the arrow, not the hand, but this little cross. I'm going to hold it down and drag it down. Good. Now I'm going to format this as a number. All right, number. And look, it's not enough sig fig, so I'm going to go to this, increase decimal places, and that's pretty good. Now for our torque. Our torque, the formula for our torque is equal to mass times g minus a times r. Our mass is this mass, 0.5. It's not going to change, so I'm just going to type in 0.5 times g minus a, which is 9.8 minus a, which is right here, close parentheses, times r. Be careful here. Some of you see radius right here, and you want to use this radius, but that's the radius of the T-pose. You don't want that radius. That's not what's giving us a torque. What's giving us a torque is the radius of the little pipe. Right? That's the thing with the string on it. The string is not up here, right? There's no torque being delivered on your T-pose. The torque is being delivered at the little pipe, at the little PVC at the base of your T-pose. So use that radius, which is 0.011. That's not going to change. Oh, I have an error. This is a very common error. Look here. I'm going to click on this, go up to this formula. So here, I forgot my multiply sign. So I'm going to put in my multiply sign. There we go. And now I'm just going to drag it down again, repeat all of my formulas. Good. And then again, I'm going to change the format into a number and add some more decimal spaces. Good. Does it make sense that the torque is similar? Of course it does, because you had the same mass pulling down on it, and you had the same T-pose, right? You had the same torque. You have the same rotational force on it each and every time, right? That should not have changed, even though our angular accelerations have changed, because our times, because our masses have changed, right? Good. The torques didn't change. The same thing pulled on it. That's fine. Okay, the angular acceleration. So that one's pretty easy. This is equal to the tangential acceleration divided by r, which is 0.011. Boom. Okay, I'm gonna drag this sucker down. Let's format it as a number. Yes. Give it some more sig figs. Good. So the moment of truth, we need the moment of inertia, which is equal to the torque divided by the angular acceleration. Boom. So here is our moment of inertia. I'm going to drag this down. Yes. And then here, I'm going to put make it a number, and then I'm going to add some more spaces. So now we need to graph this, right? So here, I'm going to highlight the radii, hold down Control so I can highlight the moment of inertia also. This is the way that I prefer, but if you want, you could do it the way in the prior video where we just copy and pasted. Make sure you paste only the values. Go up to my insert chart. So Google, I don't know why, Google loves to give me bar charts. I guess everyone does bar charts out there. But this is a scatter plot. This is an if-then relationship. So here, go to Setup, go to Chart Type, needs to be a scatter plot. Here you go. So it did set it up where these guys are my x. Let's just make sure x-axis is the radius. Sometimes it's not there. So you might need to go click on the x-axis, select the data range, and then click on everything, including the title. Right, that solves a lot of things. Right, so here, this looks okay, but it doesn't look super exponential. It might be if you force yourself, because the problem here is we didn't go through an order of magnitude. It should have gone from 0.1 meters to a whole meter, which is hard, right? There's no T-pose that big. So maybe 1 centimeter to 10 centimeters, 1 centimeter to 20 or 30 centimeters, right? That's going to be at least one order of magnitude. So that's why the data doesn't look so great. We don't have a clear exponential graph. And if you said that you do have an exponential graph, shame on you. I will find out. The best thing to say at this situation is, it could be exponential, it could be linear. The range is too small for us to tell. So here, let's at least clean up our graph. Let's go to Customize. Let's go to our chart axes and titles. Let's start with a chart title. This is our mass versus moment of inertia. Let's do capitals because neatness. Good. And then let's go through our axes. The horizontal axis, this was our radius, right? This was in meters. It doesn't really matter. It's not like, yeah, it's the radius. And then the vertical axis, this is our actual moment of inertia. If you want to put unit, it'll be kilograms times meters squared. Meters squared. Okay, good, awesome. So, oh, sorry. Let's go back to here. Let's edit the chart. And then we need to go through our series. So we go to Customize, go to Series, and then let's add a trend line. Look, the linear trend line looks fine, but we know theoretically it should be exponential, and that looks also fine. So we don't know because the range of data was so small. Okay, great. So once you have this chart, put both charts into your lab write-up. Thank you very much for watching.